a una comunidad que aparentemente parece diversa y poderles ofrecer las herramientas necesarias para poder incursionar en estos campos como investigadores, como estudiantes de posgrado, como estudiantes de licenciatura. Entonces, dado este contexto, lo que esperamos de ustedes es un trabajo arduo durante todo el tiempo que estén con nosotros. Habrá estudiantes que se integren después, que tengan un ambiente idóneo para poder realizar su trabajo, para que trabajen duramente, para que cuestionen, pregunten mucho. Esperamos de ustedes muchas preguntas a todos los que estén aquí exponiendo. Y bueno, dicho esto, pues empezamos con este evento. Cualquier duda que tengan, no duden en acercarse con los organizadores. Y aprovecho la oportunidad para agradecer de manera general a todos ellos. Son muchos, no quiero descartar a ninguno de ellos. Entonces, a todos los organizadores, muchas gracias por toda la participación, por todo el esfuerzo. Y bueno, sin más preámbulos, comenzamos. Y la primera sesión la va a presentar aquí Gustavo.
Hola. Como tenemos algunas personas que no hablan español, vamos a cambiar inglés. So now we will start speaking in English. As our first speaker, we have Chris. He's coming from UNAM, and he will be giving us a course that is very different from the rest of the program, but it's for you to have a broad perspective on what data science is and other interesting areas of physics. So, well, after that, just...
Okay, thank you, Gustavo. So I don't think I need a microphone. You can hear me at the back, right? Good. So, yeah, when Alberto wrote me an email to say, hey, would you like to come to this taller, conference, etc. It's something I used to do in a previous life about 20 years ago or so. I'm a physicist in the sense that I'm a theoretical physicist. I'm a relativist particle physicist, field theorist, many publications in that. I've done it for like years or something like that. So the thing is that Alberto knows that I do something called complex systems now, and that's very much associated with data science. And in the UNAM we have a new center called the Centro de Ciencias de la Complejidad. The thing is, I'm not so much really going to talk about complexity today. What I want to do is talk to you as a physicist. And I can speak with a bit of authority at least there. I'm not like a biologist talking about physics. And I want to talk about science and physics and other sciences that aren't physics and the concept of data. Because the thing is that if we're going to talk about data science, I want to try and get over to you a little bit about what the heck it means and why, like it says here, to boldly go where no man has gone before, Star Trek, to basically try and inspire you to see that we're living in the most incredible world from a scientific point of view. And I want to try and explain to you why it's so incredibly exciting. Everybody should be excited about their own personal research, of course. But what I want to try and do is give the big picture so you can get excited in a bigger sense. So here it is. I'm going to talk about data in science and the difference between data science, right? So that's what I want to try and get over, and basically trying to illustrate the difference, really, in some sense, by comparing the way we look at physics and the way we do science in the physical sciences versus the way we do it in other sciences. So I think these are the 4 questions I'll try and concentrate on. So why do we need data in science in the first place? Isn't all science just data science? So why do we talk about data science now as if it was something different? And then what is the actual difference? So the thing is that one thing I want to phrase the talk about is going to be in the following. It's the principal purpose of living systems and the principal purpose of science is to what? So, well, somebody can fill in a blank. I don't know if you'll fill the blank in the same way as I have. But what's the blank? Actually, the thing is that the other thing is that it's horrible to see is like fish eyes, right? So the thing is that usually what I try to do is to say the most provocative thing as possible, because if you can't respond to a really incredible provocative statement, then I don't know, I'm not doing my job, or you're not interested, or whatever, right? So please, raise your hand, say, hey, I don't agree with that. Hey, can I express a different opinion, etc., right? The idea of research is to be a two-way street, right? I'm trying to give you my opinions. They're based on my experience, they're based on my research, etc., but it's not definitive. So anyway, the principal purpose of living systems and the principal purpose of science is to my answer to that, is predict, right? Essentially, we basically say science is predict, but every living organism, even down to bacteria and even viruses in some sense, are making, right? And the real difference that we're going to see in some sense between the different areas of science and the notion of data science is associated really with how we make predictions, what mechanisms we make predictions. And in terms of living organisms, in science in many ways too, but science has kind of different goals. But to predict as a living organism is essentially to make decisions, right? So the thing is that we try to predict what's going to happen in the world, because it's important to use that prediction to make a decision, and that decision could be important for our survival. Right? That sounds a bit abstract, but it's true. Right? So the thing is that basically what we'll get to is the idea that everybody sitting in this room is a data scientist as a living organism. That we're taking data in from the environment all the time, we're processing it, we're looking for patterns, and then we're making predictions. Okay. So the thing is that what I want to do is a little bit is just think about what science means, right? And then we'll think about what the context of data is in science. And I want to think about what's the science of yesterday to the science of tomorrow. And this is where I want to basically say that something important's been happening over the last 10, 20 or 30 years, whereby we're in a whole different world from the point of view of what scientific phenomena we can examine and in what degree of detail. So the thing is that how do we do science in a nutshell, right? So what's the traditional approach? And there's nothing wrong with it, of course. So the scientific method is associated with first making systematic observations and measurements and experiments, and then formulating and testing and modifying hypotheses, right? That is the scientific method, as you'll find it defined just about anywhere, right? Okay, so where does data enter into the picture? Well, the thing is that there is no observation if you don't have data, right? Observations give you data. There is no experiment, there is no hypothesis, or there's no testing of hypotheses without data, and there's no modification of hypotheses without data. So in other words, if you're going to modify your hypothesis, you have to obtain new data to see if it's in agreement with the hypothesis. So basically, what's obvious is there is no science at all, really, in some sense, without data. Then the scientific method is three very, very important pillars. One is phenomenology. So what is phenomenology? It's a body of knowledge that relates empirical observations of phenomena to each other in a way that is consistent with fundamental theory, but is not necessarily directly derived from theory. Right? There's taxonomy, and that's the practice in science of classification, a classification of things or concepts, as well as the principles underlying such a classification. So basically, before kind of Newton in some sense, basically most of science, or not all of science in some sense, was taxonomy, just putting things into buckets and basically being able to say what thing is similar to another thing. So medicine, astronomy, chemistry, biology, etc. It's still very much driven by that. But the thing is that, once again, bringing in the notion of data, there's no phenomenology without empirical observations, which means data. And if we think of probably the most quintessential example of taxonomy is the periodic table in chemistry. But the thing is that the periodic table didn't just appear out of nothing, right? The periodic table was based on a huge amount of phenomenology from many, many, many different scientists, right? And so that needed data as well, right? So the thing is that every step of the scientific method needs data, and basically the three pillars that are associated with it, three associated concepts, all need data as well, because when we go to scientific law, in other words, we try to see when a particular phenomenon always occurs if certain conditions are present, we need data with different conditions to be able to determine whether or not it's occurring as predicted. Okay. So is there any disagreement on what science is about? Once again, I guess there's nothing particularly polemical about that. I'll get there. So that's the traditional approach. So the thing is that let's think about the modern approach. So what do I mean by the modern approach? Where you think about data science, think about data mining. So if you look up a definition of the scientific method, that's just what I gave you. If you look up a definition of data mining, you'll find it's the exploration and analysis of data in order to discover patterns, correlations, and other regularities. And it's associated with two main tasks. One is predicting in terms of identifying patterns, where you can establish causal relationships between phenomena. And the other one is profiling, in the sense of trying to understand why, what are the particular properties of a pattern that make it appear. And there are three main requirements in this sort of modern approach. One is data, obviously, and the other one is processes of that data, and the other one is inference algorithms. So what I want to basically show is traditional science and this more modern approach of data science are exactly the same things. Really, the only difference is what the data is, what the data processes are, and what the inference algorithms are. And that's what I'll spend quite a bit of the talk getting to. So the thing is that for you guys as physicists, basically your inference algorithms fall into one dominant class. So what is that? It's associated with what the worldview of the last 3 centuries has been. And what is it? It's that, right? So that's how, as physicists, we've seen the world for a long, long time. What is it? It's the world as a machine. And how do we model machines? Well, this is what we've been doing for more than 3 centuries. This is an inference algorithm. It's called a differential equation. Right? And you can have an inference algorithm that's statistical or deterministic. Nevertheless, they're always inference algorithms. I'm trying to say, hey, given the state of the world at one time, can I use this equation to find out what the state of the world, infer what the state of the world is at another time? So we model machines with differential equations. And a key aspect of that is that we all obey the law, right? So birds can fly, but they don't violate the universal law of gravitation. Right? Every single living organism is bound by the laws of physics, right? And the thing is that the laws of physics, as we'll see, basically do an amazing job at explaining a certain subset of phenomena. What I want to try and get across is they don't do any job at all about explaining a whole host of other phenomena. I want to try and quantify or try and characterize exactly which phenomena it does well with and which ones it doesn't do well with, and what the difference is between them. So we all obey the law, and there are just no exceptions, right? There do not exist exceptions. In fact, you could say that we're basically slaves of the law, right? And one of the things I'll try and get across is that in some sense, life itself is a way of escaping the tyranny of the laws of physics. Okay, so an important concept associated with that is that we all obey Newton's laws. In that sense, in physics, we have an incredibly high degree of universality, right? In other words, like I said, we're all equal under the law. But in physics and chemistry, there's really not a lot to say. Right? So everybody's familiar with the story of St. Paul's revelation and conversion on the road to Emmaus, when he was a persecutor of the early Christians, and then he became basically an evangelist, or a promoter of Christianity. Well, the thing is that I've had kind of a reverse road to Emmaus, in the sense of I'm a physicist who has now decided that there's a vast amount of science where the framework in which we understand physics, I don't think is very particularly useful. Right? So once again, you're all physicists, so I'd like somebody to get offended by that at some point and go, well, no, it's all physics, we can explain this, we can explain that, we can explain the other, because what I want to say is that no, you can't, right? And that's what research is about. It's like getting into an argument and trying to present evidence to show who's got the right side of the argument, which has to be driven by data, of course. So there's really not a lot to say in physics. So, and chemistry. So here's an example. Once you've seen one perfect gas, you've seen them all, right? We don't have to do separate experiments for perfect gases every year, every month, just in case something's changed, or we don't have to do it in Canada because it might be different than Japan, etc., right? We've done it, it's done, right? You might do it at high school just to basically learn a little bit about experimentation, but it's done. So at all times and in all places. So a fundamental thing about the physical sciences, and this is in relative terms, right? I'm not saying in absolute terms, but in relative terms, you really don't need much data, right? So in some sense, that's why physics has been so successful. You can do experiments in a laboratory and know you can reproduce the same conditions elsewhere, and it's always going to give you the same thing, and you really just don't need that much data. Right? So in other words, we can talk about big data in physics. Obviously, there's huge amounts of terabytes and up to petabytes of data that come in from climate analyses that come in from CERN, etc., And so there's a lot of data around. So what is he saying? In John, you don't need much data. So what I want to do is go along and try and explain exactly what I mean by you don't need that much data. Okay. So to the idea of data science versus traditional science, let's look at the notion of isn't all science data science, right? I mean, in one sense, it sounds stupid. When is the, what science doesn't need data? I just said, we just saw what the traditional scientific method is. It just doesn't go anywhere unless it's got data. So let's look at a very early example of data science, meaning it's traditional science, but I'm just going to talk about it in modern terms, let's call it. So Tycho Brahe had one of the first, maybe the first database, right? He didn't have an electronic database. There wasn't any computers back then. But what he had was associated with the declination. That's the basically latitude on the celestial of Mars on different dates, right? And he could plot it as a function of time. So the thing is that from that data, what Kepler did, well, remember what I said data mining was? The search for correlations, patterns, etc., etc. That's data mining. Well, in that sense, this guy was completely a data miner, right? Because what he did was he took that data and he said, well, are there regularities here, are there patterns? Well, in one sense, it kind of looks like there's regularity, meaning, hey, there's some sort of quasi-periodicity there. And the regularities that he discovered were known as Kepler's laws, right? The three Kepler's laws. So the data science here was going from data to phenomenology to taxonomy. Right? In other words, I can basically classify the orbits of the planets, etc., in terms of these laws. Okay. Then what it was Newton was the one who made the final step to basically start thinking about, well, beyond phenomenological laws, was there something, in quotation marks, more fundamental behind that? And how did he do that? Well, he decided, well, okay, he developed a motion is equal to motion. So the thing is that what he something's going around in a, what's it doing? It's accelerating. If it's accelerating and it's got a mass, then by half, that's keeping it going around in an ellipse, right? And the thing is that it would work out in some sense, consistent with Kepler's laws, was that a force had to vary, like the inverse square of the distance of the body from the sun. And when he basically got this wonderful agreement with observation. So the thing is that the three steps there were to go from data to phenomenology, and then to an identification of a fundamental reason that explained that phenomenology, which was the universal law of gravitation. And the beautiful thing there was what he did was to basically see that you could infer the existence of interactions just by seeing where something was. And this is something important to, in some sense, remember in physics, that everything, in one sense, that we've identified about the interactions, the fundamental interactions in physics, are all come by looking at where things are in space and time. Whether it's planets going around the sun, or whether it's elemental particles colliding together and seeing what comes out. Basically, everything that we know about the interactions has been deduced from just looking at where things are in space and time. Okay, so Brahe was the first, basically, person to come up with a scientific database. Basically, Kepler was a data miner, a data scientist, who mined Brahe's data to look at these inferred regularities, and then basically Newton came along and put those regularities on a footing, a fundamental law footing. Okay, so what's the difference between data now, as we think of data science, and the data of long ago, in the sense, thinking of Brahe, Kepler, and Newton? So what's the difference between data then versus data now? Well, there's been a data revolution, and essentially this is kind of one kind of way of seeing it, in the sense of how many uploads to hours of upload. This is from 2-3 years ago, so probably this is like doubled or tripled or something like that. So we're all aware of it, right? I mean, that's the thing, is that we're living this data revolution, but because we're living it, we don't tend to pay as much notice to it in the sense of what its implications are as much as we should do. But what I want to emphasize is that essentially it's this data revolution that is basically revolutionizing science itself. And to see what's revolutionary in terms of what's changing science or what's changing society, let's ask what is revolutionary then. So the first thing we can ask is that we're getting data. What type of data are we getting? And is it any different than the data we got before? So in terms of types of data, what we're getting nowadays is any different than what we've ever had. Right? We can get chemical data, electromagnetic data, acoustic data, etc., etc. That's what you could get as a human 50,000 years ago. Basically, this is like called smelling, this is called seeing, and this is called hearing. Different subjects getting this information, but that's basically every living organism is getting information of this, of one of these types, if not all of those types. And basically, get that information as a function of. So it doesn't matter whether you're a person or whether you're a satellite. Information that's in this in these different data types, right? So there's no way of getting data that's other than falling into one of the fundamental classes of that data. And so we get that data as functions of space and time, and that tells us what's going on in the no matter whether you're actually a a plankton, or whether you're a bobcat, or whether you're we're all getting data of that form, and we basically looking at this, processing it. So I remember I said that a processing center. So we get data. Processing center is basically predominantly up here, but you process data through obviously through different parts of the body too. And then we use that data to basically interpret events and to make decisions. Like, hey, where did the food source go? You know, when do I actually need to dive to catch the rabbit and not miss it, etc., etc. So in data types, there's been no difference. What about? So this is where there's been a huge change. So basically, all of data up until very recently would really have come from senses of living organisms. What we collect daily would be Google vans. Google Earth, and absolutely extraordinary amounts of data storage. The is that if you think in genome, how many bits of data do I need to store a genome? Then, depending on the size of the genome, about a gigabyte, right? It's relatively small. It's not a big data. A worm neural network, this is like a worm, is about a third of a megabyte. If you look at the different estimates, just do a Google search and you can basically look at the range of estimates about what the capacity of the human brain is, about 10 to 100 terabytes. If you look at all the books in the world, is about 30 to 50 terabytes. That's not counting multiple copies of your favorite author. It's basically just say one copy of every book. That can be fitted into that in a way we can memorize it all. But it puts it in one such. What we're generating in electronic form, basically anyway, just about now, is this. So, does anybody know what a zip is? So that's getting towards an Avogadro's number of bytes. Right? The thing is, when you do physics, you're not going to send thinking of 3 is a big number. But we're generating more or less than that. We're getting towards that kind of every year. So this is like 10 to the 12th, let's say 10 to the 13th. This is 10 to the 8th times all the books in the world, right, per year. Now, we have a big problem, right? It's much more than just comparing two big numbers. Does anybody think there exists a book that nobody has ever read? Who might have not read? Rather, who might have not read? Which book might somebody have not read? I mean, basically, it's an impossibility, right? I mean, unless you had it generated by the monkeys typing at random and eventually producing something, right? I mean, the person who wrote the book had to read the book. Maybe his best friend or his mother or his wife or husband or whatever too. But the thing is that there's nothing here that hasn't been examined by another human being. Moreover, basically thinking, hey, language speakers come in big classes, not individuals in general. There's lots and lots and lots of people who could have shared that data, right? So in other words, we speak book, right? We speak language. But the thing is that who speaks this? I mean, the thing is that when we ask the question, what information is in this, you can say, well, okay, it's 26 letters in the English alphabet, and the thing is, how many bits do I need to code that, right? And then you can say, well, this is the number of bits. And you can say, well, is it a lot of information or is it a little information? But that's completely stupid and the wrong way to look at it. You know, how much information is there in the phrase "stop or I'll shoot you"? Depending on, for instance, whether you're seeing it on a film or you've just been held up in a dark alley somewhere in a not so nice part of Mexico City. So the idea there is that basically information is completely contextual. Right? So in other words, just because you can count how many bits it is means nothing about what the real information content is. In that sense, in these 10 to the 21 bytes, we have what the content is. And much more so because we don't speak database, right? I mean, at least we can look at these and we can all be, well, that's semantic, important stuff. Or that's not important stuff, nobody likes that. You can basically, there are many, many ways to evaluate information, right? And we're in a world at the minute, unfortunately, where we've got new ways of evaluating information that aren't particularly good ways of evaluating information. But the information in these, other than counting the bits, we really don't have much idea, right? And that's one of the huge challenges of data science, of just looking at data, right? Basically, when Kepler looked at that, you know, that set of points on of the declination versus time, in some sense, that wasn't a language that was so far removed from his thinking that he couldn't basically see into that language, right? That's what we try to do in science, to see into the language of the data. But when you're talking about a database that's like terabytes of data and millions and millions of entries, where do you see the patterns? How many patterns are there? Okay. Nobody's going to go, no, wait a minute. Somebody say something. Search and processing certainly is, there's been a complete revolution. It's a very, very, very disturbing revolution because we're generating data at a far faster rate than we can actually process it. So once again, going back to the books, basically writing more books than any time in history at the minute. You just all the biography. But the point really is that somebody has read every one of those books, right? But not so database. So some of the biggest databases in the world, you know, this is the biggest, I think. So 220 terabytes of web data, 6 gigabytes of additional data. Full atmosphere watch, I think it's in Germany. So this one is 23 terabytes. It's probably so these are probably several times bigger now. Once again, I said the library contains terabytes of text data. But once again, these are all relatively teeny tiny compared to the full one. So data storage and processing is revolutionary. And basically the idea there is because of this generation, or these many new ways of generating or sensing data, then we can now track and record what is happening in the world like never, ever, ever before. So the thing is that basically, for instance, I work in financial markets. So what was a market before electronized? They became electronic. So the thing is, if you wanted to buy something and somebody wanted to sell something, you have to get together in a market, in the bolsa. And the thing is that something would have to be written down on a piece of paper to say this guy bought this from this guy who sold this for this price, right? There have to be, what was the medium by which it was done? It wasn't all done on just, oh, I'll remember that, right? It had to be written down, right? It was written down on in paper. But obviously there's a limit to how many trades you can and you need a person to write it down. Right? So how fast people, how many people you have to write things down. The person goes click, and the thing is timed to essentially milliseconds. So the thing is that you can see, hey, you know, when this person was buying, which person was selling. So it's the computer that basically does all book keeping now. And the thing is, it does it so that you could be looking at essentially hundreds of thousands, potentially, of trades per second, right? Something that humans could never ever have. However, it's now in a form that's sitting there in an electronic database, so that in principle, else in data. If the data other degree of information is in there. Okay. So what well, data connectivity is years ago, 10,000 years ago, whatever it would be, in the sense of there isn't any, meaning if you wanted to have data connectivity before there was actually a system of sending a message from one, well, I mean, basically everything was just by a human being going like, hey, the king says you need to do this, right? So the thing is that the connectivity was limited by basically the speed of humans. And the thing is that in that sense, even horses didn't really improve it. I mean, in the sense of for very long distances, a human was probably about as good as anything. But now, once again, we have a relatively speed, what looks like an incredible degree of connectivity, right? So we're not just connected by basically to be in voice range, so we have to be in physical contact in that sense with somebody. We can be in contact with whoever we want in the world as long as they've got some apparatus that can basically allow us to communicate one with the other remotely. But what I'd like to ask is just, okay, it looks like we're incredibly connected, but let's just ask, just how connected are we? So the thing is that if we think of the universe of all data, like it was an iceberg, then the thing is that my data, that basically I have access to, batteries, is basically just a little snowflake right there at the very, very tip of the iceberg, right? And the data I have access to is much, much bigger than that, right? I mean, I can go online, I can Google things, and it looks like I have access to an absolutely incredible amount of data. And relatively speaking, I do have access to an incredible amount of data. But compared to the 1 zettabyte, basically what I have access to is a teeny, 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 tiny fraction, right? I mean, basically all the data in the world for any one of us, even for someone like the CIA or something like that, they can go down here a bit further than us, but the vast majority is still inaccessible to them. Right? So we live in an incredibly connected world in one sense, but from a data point of view, it's not as connected as we might think. So it's revolutionary in one sense, but there's still a long way to go. And one thing there that's from, let's call it a scientific politics of science or the ethics of science that's very important is this idea of what's public versus private data. Right? We've already got many debates about that, and that will continue. So, what else is revolutionary? Well, our capacity to search data has basically increased exponentially. So, what was the first search engine? The first search engine was me walking over to somebody and going, "Hey, Gustavo, where can we find a cup of coffee?" And the thing is that you'd hope that the person that you talked to could provide the knowledge that you didn't have. That was the search engine, right? And so the thing is that you were limited by who you could go around and basically hoping that you could find people who knew more than you did, right? So the thing is that we've always, since the dawn of civilization in some sense, had specialization in the sense of knowledge specialization. The other priests, they knew all the thing about what was going to go on with the calendar, etc., and they kept the knowledge to themselves. The whole point of a guild, a gremio, is like, hey, we got the specialist knowledge and you don't get it, you have to come in and join us, right? Knowledge is something that's been used as an object of great value and protected many times. And that was the only thing you could do with knowledge among the people who actually had it. Obviously, once things became written down, then the second search engine was to basically find a text that contains what you want to know, as opposed to finding a person, right? So what that meant was a person could put their knowledge into a book, and that book could be put in multiple places, and then you could go to that book as opposed to going to the person. Now, the thing is that you're probably all too young. Well, who goes to the library? Do any of you students use the library at all, or you just sit at your laptop? I mean, I haven't been. You use a library.
I take my laptop to the library.
You take your laptop to the library. But you use the library to look at books, or to just use your laptop there? I mean, the thing is that it's nice to go to a library just because it's nice to look at books. But I haven't been in the library in my institute for, I don't know, 15 years or more. Right? I mean, the thing is, I love books, but I'd love to read them in bed or something like that. I mean, the thing is that I don't really use them at all for work. I mean, the thing is that, you know, just think about how incredible just Googling, you know, I remember when Google first came out, students said to me, hey, try this thing. It was just a little box like it is now, and you put in thing, and then out came these results that showed you, hey, some knowledge that you were looking for, some that you weren't looking for, and the thing is that's completely different than basically looking for a particular book and then hoping you can find in that particular book what you're looking for. In other words, the fine-grainedness of the search is so incredibly higher, right? So in other words, you can look for books on quantum mechanics, you can look for a particular book on quantum mechanics, but you can't look, or you couldn't look before, for a particular section about a particular thing in that book, unless you went to the section, and then now we can just put in a text string, and you can look in all the books that are at least online. So in that sense, that's been a huge. Probably better. Yeah. Okay. So data search capacity has certainly increased exponentially, but we can also ask just how good it is. And this is from a few years ago. I mean, it's a lot better now. The incredible thing about Google is it uses us to get better, right? The other thing, it can be dangerous, because if we put biases into the system's stupid enough to just believe the biases, right? But the thing is that it's basically counting on the fact that human beings are clever enough, and if there's enough of what we're looking for, it's not going to be so biased. So the thing is that if I ask Google what are the longest rivers in the world, or the longest river in the world, then it'll come up. Just like semantics to that search is very, very simple. If I put in this one. So I put in early Victorian educational reforms. So that's reformas educativas en la época victoriana temprana. But the thing is that Victoria is also a state in Australia. And so the thing is that they got pretty confused, wondering, well, was I looking for things about Victoria in Australia, or was I referring to Queen Victoria and a particular period of British history? It's actually now a lot better. But once again, the reason it's a lot better is that we ourselves have trained it to be better by the amount of different searches that we've done. But at the end of the day, I mean, this is a huge area of research, and it's going to get bigger and bigger and bigger in terms of just the semantics of search, right? So basically, how intelligent can machines be in understanding what they're looking for? I mean, there's a famous system at the minute that costs millions of dollars called Watson by IBM, and big hospitals, etc., rich hospitals are buying it because you can put a pile of data in there about all medical journals in the world or something like that, and so it's basically doing supercharged Google from the point of view of a bit more semantically relevant, right? You can basically search looking for weird diagnoses among all these past cases and all these medical journals, etc., etc. But it still doesn't understand, not in the same way as a human being understands. So basically, Google is fast, but it's not clever. And the thing is that there's a huge amount of debate now about deep learning, and every now and again there's a big surge in artificial intelligence marketing. For instance, the most recent one, well, two. One was, I mean, everybody knows about Deep Blue, right? The computer, IBM computer, the big Garry Kasparov at chess. Well, that's a long time ago now, but they developed a computer with deep learning that just beat one of the best players in the world in Go, right? And they always imagined that Go was so much more difficult in one sense than chess. But they imagined that, well, a machine, it'll take decades to come up with a machine that will beat a human in Go. And the trouble is that it's the wonderful thing about stepping into a new field from a previous field. As a physicist working in computer science, all the people in artificial intelligence, I kind of say, well, I'll be impressed when that computer can basically plug itself in, basically reproduce itself, and then answer and play other games, or basically learn to play other games, as opposed to just being one good at one thing, right? So it's an achievement in many ways, but it's not remotely comparable with biological intelligence, let's call it. So humans are wonderful at semantics, and machines aren't. So what's revolutionary? We can think about data communication speed. Well, yes and no, right? I mean, in one sense, we haven't had an increase in data communication speed for like well over a century, right? Once we started sending telegraph signals, well, you can't go faster than the speed of light. So basically, that's a limit, and it doesn't change. It can't change. So we're not getting any faster in terms of communication speeds. The other one I think is important is back to this idea of what's the purpose of data. The purpose of data as living organisms is to make decisions, right? And that's always been the case, and it's the case there now. Really, in some sense, a lot of data science is associated with like trying to predict who's going to buy my product, for instance, right? Or who's going to vote for this candidate. There's many applications. Some sound scary, some less scary, but they're always used to take decisions. In that sense, there's always been an evolutionary pressure, let's call it, in favor of those who can record, process, store, and analyze more efficiently and more precisely data in order to make better decisions. So yeah, I would almost state to you that in one way you can think of natural selection, Darwin's theory of evolution, as just a way to produce better data miners, right? Meaning, hey, organisms that are better at taking in data from the environment, processing that data, and then coming up with more effective decisions in a given environment. So data analysis, well, yes, that's changed an awful lot too. Once again, in biology, as I just stated, natural selection is basically a selection pressure on data mining capacity. Basically, instinct is essentially hardwired data analysis, meaning, hey, it's in your genes about how to react in a certain data configuration and in the sense of taking a decision. If I touch something really hot like that accidentally, I really can't avoid doing that. That's basically a reflex that's in some sense pre-programmed in the genes. You can also learn, which is basically adaptive data analysis, like learning a game. And basically, see machines that can do that now. They can do certain tasks. They can do certain tasks much better than we can. But in the context of that 10 to the 21 bytes, this is where the future lies, in the sense of how do we automate analyzing and finding what information is in that data. Once again, for big physics experiments like CERN or LIGO or things like that generate a huge amount of information, then the point would be is that there's already an interface with, let's say, this more modern version of data science to basically try and extract patterns, etc., from that data. But once again, it's not a big deal compared to the idea of this what's in that 10 to 21 bytes. So what does all the data from this data revolution represent? So this is something that I think is important to get over. Of that 10 to the 21 bytes, let's call it, what fraction of that is basically scientific data? Meaning generated in a scientific way, in a controlled experiment, etc., where you can trust it. You can think there's, we've tried to eliminate data biases, etc., etc. 10 to the 21, well, effectively zero. Basically, what that data represents is complex adaptive systems. So what are complex adaptive systems? We are, right? So an awful lot of that data is associated with us. I mean, think how many megabytes of data we all generate now in a year just in pictures of ourselves, right? How many oodles of data, how many oodles of selfies exist on the planet now? So, and the thing is that it's kind of, in one sense, it sounds kind of sad, but in another sense, it's probably telling us something deep about human psychology. And the second thing is there's actually useful ways to do science about these things. I remember in C3, somebody telling me about a study carried out on Facebook where they were looking at tourist pictures of zebras in East Africa, and they, by analysis of those photographs, they could basically start to work out things that weren't so much known about zebra social interactions, right? So the thing is that, so they're just by, there's nothing scientific about that, in the sense that that data was not produced with a scientific experiment in mind, whereby some zoologists went to East Africa with the sole purpose of studying zebras. It was just a case of, hey, people taking a picture on safari and then put them on Facebook. Well, there's basically a database, let's call it, of pictures of zebras that can be useful for science. So what do we do with all this fragmented, restricted, dirty data about the complex adaptive systems? How do we analyze it? Well, this is where this, we get back to this very, very strong difference between the physical sciences and let's call it the non-physical sciences. The difference in the physical sciences, relatively speaking, again, there's not much to say from a data point of view. But in complex adaptive systems, there is almost an unlimited amount that you can say. So imagine what you can say about a city versus a crystal as big as a city. So the crystal as big as a city, what are you going to say besides its crystal structure and its size? Right? So there's not much to say really beyond that. What can you say about a city? Well, you just go on forever and ever and ever. Right? I mean, the fundamental difference between these two situations is here you can enumerate the states. So basically, when we go back to these things about what are the foundations of physics, the physical sciences almost inevitably deal with a configuration space, alternatively a phase space. But you need to know, hey, what are all the possible configurations of my system? So what are all the possible configurations of a city? I don't know. What are all the possible configurations of a human being? I don't know. So the thing is that there's a huge problem there in the sense of how do you even begin to think about putting into a more quantitative framework describing your system. So, and this is essentially the difference between big data and deep data. So when I say deep data, so you can talk about basically phenomena at the level of the entire city. You know, what's the crime rate for the city? What's the economic output of the city? What's, you know, basically very, very macro variables. But you can go down to multiple, I mean, we just see it in political and economic structures. There's multiple hierarchy of different levels, all of them relevant. And the thing is that there's feedback loops between all those different levels, right? So what it means is that there's an incredible depth when we look at some phenomena like that in social systems or biological systems. But when we look in physical systems, you might think, well, you know, we have that in physical systems too. Well, the thing is that, you know, here I have a glass of water. Well, I can look at the glass of water. I can talk about it in terms of fluid dynamics point of view. But then I can go down to, say, the molecular point of view. Then I can go down to the atomic point of view. Then I can go down to the nuclear point of view. Then I can go down to subnuclear. And then you stop. And you might think, well, there's some depth to that, right? Well, not really. And the reason why, and this is the only reason in some sense why physics has been so successful, each one of those levels couldn't care less about the other level, right? Imagine to explain fluid dynamics, you had to know about the nuclear properties of oxygen and hydrogen. Well, we wouldn't have been able to do it, right? So in other words, basically physics is based on the fact of there are scales that are completely separate one from the other, whereby the phenomena at that scale can be described by an effective theory at that scale and couldn't care less about what's going on at another level. In fact, you know, one of my big main area of research many years ago was called the renormalization group, which is about the only general theory that at least made an attempt theory at one level from a level below it. But in general, right, so I think so let me basically, once again, be provocative. There is no theory of molecular physics that comes directly from atomic physics from first principles. It doesn't exist, right? Nowadays, because we have nice big computers, we can put basically simulations in and see phenomena emerging, but that's not the same, right? So the thing is that in the non-physical world, there's an enormous depth to different structures, and moreover, they're all communicating one with the other. Right? Whereas in physics, there's a limited set of structures, and the point would be is they're not really communicating one with the other. And once again, that's the reason why we can do the work of physics. Once again, imagine if Kepler was trying to do his laws where, you know, quantum mechanics was important for planetary motion. Well, you wouldn't have got very far. Okay. So it's important to remember you can say a lot about complex adaptive systems, and each thing you say depends on a lot of other things. So physics is, so imagine that we're doing science in a general sense of what I want to do is I want to predict something as a function of something else, right? So the thing is that in physics, what we're used to doing is predicting one thing here as a function of another thing there. It might just be, hey, what's the position of what probability of the position of a particle at time t given at time t prime, right? That might be a simple example. We don't tend to say, hey, what's the probability of position of a particular particle given the positions of many different particles, right? What we do in that case, instead of saying one particle here and one particle here, we say, well, I'm going to take a summary of all the particles on this side, and I'm going to take a summary of all the particles on this side, and what's my summary going to consist of? You know, a variable that I call pressure, or a variable that I call temperature, or some macro variable like that. But in complexity, so in basically in the non-physical world, imagine, so a lot of my research now is associated with obesity and diabetes. Imagine I'm trying to make a predictive model for obesity. But what do I have on this side? Well, basically on this side, everything, right? Every gene that you've got potentially, the epigenetics associated with those genes, what your mother's nutrition was when you were before you were born, when you were still in the womb. Basically, how was your childhood nutrition? What's your personality? Which in turn depends on the genes, but not 100% on the genes. Psychology, sociology, campaigns of the food industry, politics of the health department. It's basically nothing. We have no idea how it goes in, right? That's why big data, or basically this data revolution, is so incredibly insightful. We can even begin to think that we can start to put that data in on this side, and we could never ever do that up until the last couple of decades. But the true challenge is to go beyond saying, hey, what's the problem? Given all factors, it's the probability of somebody being obese or having this problem with the lungs or that. So in other words, what I said was, for a complex system, there's many things you can say about it. Well, here, I might imagine I'm just saying one thing. Are you obese or aren't you obese? But that's not a full description of the system in that sense. What's a relevant description in terms of many different properties? And then how do I describe basically the simultaneous state of those different properties as a function of all these other properties? You know, we're going to be working on that problem for generations and generations and generations and generations and generations. The commas will be still here. Okay, so in other words, there are many effects, many causes, and basically we go from the micro to the macro. And the thing is that the huge challenge for science itself, from that point of view, is that involves many disciplines. So why is that so? So the thing is that, back to the thing about physics, molecular physicists won't normally talk to atomic physicists. Why do they need to? Atomic physicists won't normally talk to nuclear physicists. Nuclear physicists won't normally talk to particle physicists. Why do they need to? Right? Once again, there's this shielding of the different levels. But if I'm saying, hey, I want to get a better idea on obesity, and here I should be looking at comunicólogos, or marketing people. I should be talking to sociologists, I should be talking to psychologists, I should be talking to geneticists. There's almost nobody I shouldn't be talking to. Right? Where do we have science like that? Well, we don't. But we try to be in that situation. So the data revolution is revolutioning our ability to study the immensely rich phenomenology of complex systems and construct more appropriate taxonomies. So this is just very briefly to try and say what really, in some sense, characterizes the phenomenological level, complex phenomena from non-complex phenomena. And really, we can paraphrase that by saying what differentiates between sciences. So basically, the thing I would state here is complexity does not exist in the physical sciences in the way I want to characterize it, only in the non-physical sciences. So the thing is, in terms of structural properties, there's a hierarchy of many different scales. Well, we kind of have that in physics, but as I said, it's very different in the non-physical sciences because of all these feedback loops, etc. And we have effective degrees of freedom. So these two here, kind of what you also see structurally in the physical world, and hierarchies of building blocks and interactions that are stronger, intra-block and inter-block, etc. So in other words, the interactions at the atomic level are stronger than what they are at the molecular level, right? Now, this is basically the thing that doesn't exist in the physics per se, that the different levels aren't linked in the same way as they are in complex systems. But it's really these that really are the distinguishing type. In one sense, in physical systems, there's really no notion of function, right? What's a particle for? Well, it isn't for anything, right? But the thing is, you can say, well, you know, kind of what's a lion for? And you can characterize what a lion's for by many different ways, in the sense of what's its place in the ecology, what's it doing, etc., etc. But essentially, all of those ideas about functional properties are associated with what something does. Right? There's really no notion in physics of something doing something. Right? But the thing is that I'll give an example, a specific example of that in a second. So it's also a dynamics that depends on many different rules or strategies, and I'll give an example of that too. So what does this mean? It means that in the physical sciences, there's only one rule, right? There's Newton's second law at this scale, and that's it. You know, you don't have to be thinking about there's Newton's second law and Newton's 2.1 law or 2.3 law, and whether you apply 2.3 or 2.1 or the second law depends on your state. Well, that's what happens exactly in non-physical systems. Basically, they learn. There's no idea of let's call it learning and adaptation in the physical sciences. And also, I think a good way of basically looking at the distinction between the two is the difference between the city and the crystal as big as a city. So in other words, the behavior, let's call it, of a complex system is just much more complex, meaning it is incredibly richer than a physical system. And that's why I said physical systems don't need much data, relatively speaking. They're phenomenologically poor relative to non-physical systems. Okay. For many years, I kind of puzzled over the fact that, well, in that sense, is complexity a scientific concept? So what do I mean by that? So the idea is in science we need data, and data is associated with observation, right, or experiment. So we need a way, in some sense, to measure, right? What's our complexometer? How are we going to measure complexity in that sense? What's a good measuring apparatus? Well, basically, there's two areas where I think you can characterize complexity in a way that's pretty unambiguous, meaning satisfying all those characteristics that I said, and also where I think we'd all agree intuitively that they're complex. One is biological complexity, just means the second one is in human languages, right? So basically in human languages, there's symbolic complexity, meaning there's structure on many different levels, and those structures are basically interacting at multiple scales, right? So from the point of view of grammar, basically the interactions between different elements in a text is very limited, right? Basically it's restricted to what's in the sentence. But once you're talking about semantics, in other words, meaning, then you can have the first sentence of a book related to the last sentence of a book, and with many, many different intermediate levels. So it's basically semantics that just links everything together and makes it complex. So the thing is that this is basically what I would like to say is a complexometer. So from the point of view of symbolic complexity and the complexity that's inherent in language, these are very, very good things at detecting that degree of complexity. It's back to this thing about what is the information content of a particular text, of a piece of human language. We can basically examine language, and the thing is that depending on the degree or what the language, what it was about, the text, you could find groups of people that would have a large degree of overlap and agreement about what it said. In other words, we'd all be measuring more or less the same thing. So basically we can ask how good is your measuring apparatus. Well, the thing is that, once again, the online translation systems are much better now. This is something I did a few years ago. If you do it now, it still gets screwed up with Japanese. But what you can do is, so this is the first line of Hamlet's famous soliloquy in Shakespeare's play, to be or not to be, that is the question. And what you can do is you can just put it into a translating machine and say, translate this into Spanish. Then what I'm going to do is put that Spanish in and say, translate it back into English and see if it gives a closed circle, a closed loop. Right? So basically, with Spanish, it comes back to the same thing. With Dutch, it comes back to the same thing. But if you put Japanese in, at the first iteration, it gives you back that because of a certain or because it is not it is question. And then, so basically, you can see that there's a positive Lyubimov exponent here in a sense of just diverging further and further away from the original thing. What that's telling you is that this thing measures complexity, but the thing is that it measures it well in a particular language versus not in a particular language, depending on how it's calibrated, right? If you look at what you look at Google Images and say Spanish, that's what comes up. Then the thing is that you would expect good measuring apparatus for this, but this Japanese speaker who doesn't speak any Spanish at all to be a bad one, and vice versa for the Japanese. Right? So in other words, the claim is that this is a measuring apparatus, but then you go, well, yeah, but the measuring apparatus, what it measures on its calibration, right? Meaning on the language that you speak, etc. As among other things, right? Meaning your educational background, etc. But the thing is that this is no different whatsoever than in physics, right? We shouldn't think, this sort of thing is very subjective, whereas in physics things are very objective. Because if we look at what we do in physics, imagine that I have two phenomena, basic electroencephalogram and basic or boiling water, and I want to basically say, okay, I want to basically measure these two phenomena. Right? So the thing is that what am I going to use? I have a voltmeter here or a thermometer. What's the best way to find out what the temperature, what this water is doing? Is the thermometer better or is the voltmeter better? Well, does anybody think a voltmeter is better? This is the Spanish, this is the Japanese. Right? It's exactly, this thing will react if you put it into a big enough pan of boiling water. Right? It will get hotter, it will not work. There will be a relation between these two phenomena. The only difference is it's not calibrated, right? Just the same if I try to use the thermometer with voltage changes in electroencephalogram, it's not going to be particularly useful. So in other words, basically, all of science is about having a measurement, which is a correlation between two phenomena, but having the measurement correlated, so that a change in this phenomena, I can see a corresponding change in this phenomena, right? So basically, when we're talking about our native group of speakers, and we basically change the text from one thing to another, we can all pick up. We're all calibrated to pick up, it's now changed its meaning. It might be slightly different. Well, it's the same, right? Slightly different thermometers, slightly different measurements. It's not different. Okay. So what I want to do is say about mathematical modeling, right? So there's an awful lot about physicists everywhere, right? And the trouble is that physicists think they know it all, right? I thought that we were the worst for that, but probably doctors are worse than physicists are almost. But the thing is that there's so much work done in, let's call it, complex systems by physicists. And the thing is that the vast majority of it by physicists going, well, this worked here, the work here, right? And so I guess that's what I want to say that isn't true. So let me look at a typical example. So to make a mathematical model of a dynamical system, like I said, you need a space of states, right? That's an absolutely fundamental staying with the traditional. And we also need update rules that tell us how to get from one state to another, right? That's what physics is about. I state my configuration space, and then I say, here's my Newton's second law that tells me how to get from one state to another. Okay. So we boundary system, and next there's many important applications nowadays. How does it change the nature of the phase transition? Because you can't have this diverging susceptibility. So imagine that you have a film, right? So a thin film. So the thing is that if you look at dimensions that are very big compared to the microscopic scale, much smaller than 3 dimensions. But if you look at scales that are big compared to the film thickness, it looks like it's 2 dimensions. And the thing is that one of the things in terms of universality with all the theories that we have is they're fixed in the dimension. You say, hey, I can do three-dimensional physics, I can do two-dimensional physics, but how the hell do you do what's in between? And so we worked out a way of doing a renormalization group, looking at this, how a particular set of scales integrated from, so in other words, when we had a system so that when you looked at it interpolated from looking like three-dimensional system at one scale to a two-dimensional system at another scale. So in that sense, you go from an effective field theory in 3 dimensions to one in 2 dimensions, right? And so the thing is that we could actually follow that, but the thing is there's no renormal follows atomic physics into molecular physics. That doesn't exist. There's no renormalization group that basically goes from quarks and gluons to hadrons. It just doesn't exist. Okay. So the idea was this. This is basically a model from on the front page of Nature quite a few years ago. A guy who I know well, who was at Princeton. And basically what this represents is the direction vector of a point particle, and it's just a difference equation relating that direction vector for the I particle at t plus delta t to what it was at t, where basically c is the position of the particle at t. And so this is a sum over the line, and basically this is its velocity, and basically these two terms represent essentially an attraction and a repulsion between the particles, right? And so the thing is that this is kind of the standard as a physicist in the sense of thinking of like interactions between point particles in a gas with more realism than a perfect gas. Meaning, hey, at short distances you have repulsion, and at long distances, the longer distances you have an attraction, right? And so we can ask, does this represent a complex system? Well, you wouldn't at first think, at first sight, think so, because hey, you know, just like many other sets of equations that we have in physics, that like a gas with some fairly standard interactions, and you wouldn't think it was that, but this is what it's supposed to represent. So this is a fish shoal, and those equations are basically supposed to represent the directions of these fish. So when the fish are very close together, they repel, but the thing is that there's an attraction to try and align their direction vectors, right? And the thing is that you could look at those equations and integrate them numerically, and you find as a function of the parameters there that there are basically bifurcations, so that beyond a certain limit, they're basically just moving randomly, but on the other side of that limit, they form a shoal, right? The thing is amazing that we can describe complex systems using the traditional method of physics. Well, you know, I go, no, you can't. The reason why is the following. It's not that that's wrong, absolutely not. It's right, okay? But it's important to distinguish between a description of complexity and a non-complex description of a particular phenomena or behavior associated with a complex system. So in other words, we have been describing for a long time, but just certain particular characteristics of those systems, and the characteristics where the complexity, in the sense of this interaction between all the different scales, doesn't end. For instance, you know, there's nothing in those differential equations that's telling you why those fish are doing that, right? So, and why beyond a certain parameter they do it and they don't do it, etc., etc. So basically, a set of equations like that is just, in one sense, glorified curve fitting, right? I mean, basically looking at a particular dynamical phenomena and trying to curve fit to it. And, you know, it's kind of respectable, but it's not telling us anything about them per se, in the sense of why, say, it occurs. I mean, that's another difference in physics, right? You know, why Newton's second law? Well, why, right? Why the second law of thermodynamics or the first? They're just the laws of physics. But in basically evolution, you can keep going Y. Okay. So basically getting a bit towards the end now. So the predictability, so the thing is, the one thing I want to emphasize is when we talk about data science and traditional science, in the sense of that uses data, basically a lot of the differentiation between them, about how we're using it nowadays, data science, is really to do with the type of phenomena we apply it to, but the type of phenomena we apply it to is very much associated with this notion of different ideas of what predictability means, right? So in other words, predictability, remember, I said that we're all slaves to the law, right? That's predictability in the physical sciences, right? So the difference between complex and simple systems, so if you want the difference between physical systems and basically social or biological systems is the difference between being and doing. So what the hell does he mean by that? Okay, so what we'll do is we're going to imagine the following experiment. I'm going to take a cat and I'm going to crush the cat up into a ball. So it's exactly got all the molecules of the cat, right? And then what I'm going to do is I'm going to put the cat, I'm going to imagine I have cloned cats, so they're absolutely identical to the last molecule of the cat. I'm going to put the cat in this hand, and I've got a ball in this hand, right? But what I'm going to do is I'll turn the cat feet upwards, and I'm going to drop the ball, and I'll drop the cat at the same time, right? So what happens to the cat?
It lands on his feet.
It lands on its feet. What happens to the ball? No, I'm not talking about after it hits the ground. So the base, what does the ball do? It falls. But is the cat falling? Right. Basically, the ball does nothing relative to the cat. So basically, the center of gravity of both these things follows exactly the same trajectory. Right? Both are slaves to the law. Right? The thing is that the cat does that. So what the hell has it got that allows it to not be as boring as the ball? And that's the miracle of basic complex adaptive systems. That's why the physical sciences are completely different than the rest, in my opinion, and why one really, when you talk about these phenomena. So this is a mechanistic approach, this is an adaptive approach. The cat obeys the same laws of physics as the ball, but it's not a slave to it. So basically the evolution of function, so when I say function, is that basically doing that has a function. Right? We know it has a function because in some sense natural selection is basically acting on that function. Right? Presumably in some ancestral past of cats, there were cats that didn't do that and they ended up with more brain damage than the cats that did do that, and that's what you call a selective advantage in a Darwinian sense, and one survived versus the other, right, in differential survival. So basically, the evolution of function, the function of being able to turn over and land on its feet, but in more general terms, that's the revolution that allowed to escape the tyranny of the laws of physics. And basically, all of complexity as we see it is a consequence of that revolution. So I'll give an example of that. That's kind of cool in a second. But another way to put it in more formal terms is in biological, economic, social systems, etc., organisms exhibit a great diversity of strategies. A ball doesn't have a strategy, right? Its only option is to fall, right? So the thing is that a ball doesn't make a decision. Now the thing is, you might say a cat doesn't make a decision in the sense of, well, it's instinct. But obviously there's a great deal of variety about cats that are doing better than others, etc., etc. But moreover, if you think in the bigger picture, there were decisions made at the macroevolutionary level, meaning, hey, there were cats that did it and there were cats that didn't do it in the ancestral past of cats, right? And so the thing is that, in one sense, an adaptation that an organism develops is in some sense a decision, right? I'm not thinking of decisions in terms of, hey, should I go to the movies tonight or not? We're thinking about decisions being as just alternatives, right? So there was an alternative for cats. Cats could have fallen on the feet, or they could have not fallen on the feet, and one was preferred over the other. And the thing is, we all imagine that we think of decisions like free will. What I can tell you, you don't have free will. Right? Basically, 99.99999% of everything that happens in you is just autonomic, right? So, and the thing is, all the part that we think is free will, in the sense of, oh, I can give up smoking, I can not eat bad food, etc. Neither is that free will. Right? And basically, that's a lot of my research in that area to understand is probably there from an evolutionary perspective. So the dynamical state, so because of the strategy thing, the dynamical state of any one depends not only on the state of the individual at other times t, in the sense of its configuration, but on the strategy or updated rule selected at time t. And that in turn depends on the rules of others at time t. So you have to work in a space of states and a space of strategies or rules or models. Right? This is a whole new different ballgame. And you might go, well, isn't that a bit like game theory, like rock, paper, scissors? Here I have a game of, I have a system with 3 possible strategies, scissors, or rock, or paper. Well, it isn't. And the reason why it isn't, because no idea what the strategies are. Right? Imagine if you were like playing God 4.5 billion years ago, and scratching your head and thinking, I just had a great idea. I'm going to call it lion, right? And the thing is that then you got the problem, well, I've just had another great idea. I'm going to call it cockroach. And the question is like rock, paper, scissors. Does lion beat cockroach? Or does cockroach beat lion? Does cockroach beat human? Or does human beat lion? Etc., etc. It's just a useless point of view or a way of thinking when you go to that level. That's not to say it has no place whatsoever in a small-scale evolution, but when you think of the big picture, it's no use. We have no idea what that space of possible strategies is. Okay, so to give an example of this thing of being versus doing. So what this is a simulation done quite a few years ago now by a guy called Carl Sims. And what he did was the following. So he did it in the computer in terms of creating a virtual world. But in that virtual world, he put blocks in there, right? And because it was a world that followed the laws of physics, laws of etc., what he could do is he put 2 of these blocks together, random, but they'd be joined, right? And because they were joined, then that restricted them in their motion. So what he did was, hey, there's my physical restrictions. Law, the slaves to the law meant, hey, once they were joined like that, they couldn't do something else. They had to do that. But what he did was, in the spirit of a genetic algorithm, just to recombine and mutate, you put a new block in, you join these 3 blocks up with these 3 blocks, etc., etc. And he put a fitness function in there so that the better they swam or walked or whatever, the more likely they were to have offspring, right? And these are some of the things that he came up with, right? So the thing is that there, at one level, when you think of 2 blocks doing that, you go, I can understand that. Physics is okay there, right? But the thing is that you get up to this level and you go, this thing is swimming along. No. So just in that very simulation itself, it contains the essence of this thing of physics going from an explainer to just a restrictor, right? So remember, for the basketball, it's an explainer. It explains the whole phenomenon, right? It doesn't explain why the cat does that, right? It's just a restrictor. It means the cat can't violate the laws of physics, but it doesn't explain why he does that. So it's just the same for these 2 blocks. It explains, hey, that's why the blocks can only do that and not something else. But it's not an explainer once you get up to this level. It's a restrictor, right? You can't have any of these block combinations that aren't obeying the laws of rigid body mechanics. Okay. So basically, complex adaptive systems do things. Another way to say that is to basically make decisions. Once again, a ball doesn't make a decision to fall. A cat makes a decision, not in the sense of free will sort of thing, but it makes a decision to fall on its feet. So what are some I think this is probably a bit heavier than this, especially with the adding. Okay, so I think I'll drop these, and which one do you think? Who thinks this will hit the ground first? Who thinks they'll both hit at the same time? Okay. The thing is that, you know, last time I gave this, I gave it to some social scientists, so I had a rude awakening on some elements. Right, okay, so they both hit at the same ground. So my prediction was 0, 0, and 100%. Right? So you were very predictable people. Okay, so the next one is we have two options. I'm going to act with a force on this object with my hand, and we're going to ask, is it going to move or is it not going to move? Right. Who thinks it's going to move if I apply a strong force? Okay. Yep. So I predicted that 100% would say that it's going to move. So the thing is, what am I predicting here? I'm predicting your familiarity with everyday phenomena, but from a physics point of view. When I was doing it with social scientists, in fact, quite a lot of them didn't get this right at all. Right? So this they understood, you know, this they understood, but they obviously hadn't read about Galileo's experiments at the Tower of Pisa. Right? Okay. So the thing is that I'm 100% correct at the minute, right? So now we're going to keep going. So you haven't had a drink of water or any liquid, and somebody offers you a litre of water or a box of cornflakes. What are you going to select? The water or the cornflakes? Who votes for cornflakes? This is a serious game. So 100% water, 0% cornflakes. So it's not even physics now. I can predict exactly what you're going to do in the non-physics arena. Okay. There's in the auditorium, and the alarm goes, and I ask if you want to stay and listen to the end of the talk and head for the exit as quick as possible. What do? You run for your life, or you stay here. Right? So who stays here? And once again, you know, don't try and.
I stay to see if you predict I would.
Yeah, that's why we complex adaptive system. So I should have put 99.9%. So, but the thing is that natural selection would be against you, unless you already have children. Okay. Finally, you're very, very hungry, and somebody offers you 1,500 calories satisfied. You can either have 7.5 kilos of celery, or the food of your choice, right? You know, whatever you like. I mean, there's anything you like, right? It doesn't have to, if you're vegetarian, it can be the nicest vegetarian nut loaf or whatever you like. But what would you have? 7.5 kilos of celery, or something other than celery, right? So who goes for the celery? So 100%, 0%. So basically, we're up to 6 questions now, and I'm 100% correct on predicting human behavior and human decisions. Okay. Right, so we'll make it a bit more interesting. Water in 3 days, and somebody offers you a litre of Coca-Cola or a litre of Pepsi. Okay, now everybody vote, right? So who would go for Coke? Okay, who would go for Pepsi? I'd say that's about 80-20. Right? So let's see how well I did. Coca-Cola, Pepsi is 70-30. I'm close, right? So where do you think I got that? Got in previous experience with other audiences, you know, maybe physicists in Lyon are different. Or I could just Google it and find out what the relative sales of Coke and Pepsi are in Mexico, right? That could be another way of doing it. And then I'd be thinking about whether you're a representative sample of the Mexican population. Okay, so once again, it's a big fire, and you've got to the exit on time, but you notice that somebody's trapped in here, and we'll pretend it's not me. Would you come back to help them, risking your own life, or would you keep running? How many would come back and help? Okay. And how many would keep running? No, that's about, I'd say 50-50 actually. So if I'm kind of surprised, I expected more to say they probably stay, because then I'd go some of you are liars, right? Because that's actually a fact, an important fact for all the research I do on obesity and diabetes. We're big liars, right? We lie about everything. We lie, oh, I'll do that, yeah. Oh, and you'll never do it, right? So, but we like to think that we well behaved and we do the right thing, etc., etc. So once again, 50-50 was about that. So isn't data science an impressive subject, right? I mean, I'm showing that, hey, I can predict very, very well. And, and we're going beyond the easy stuff now. Now we're getting into the hard stuff, and I'm still doing a good job. Okay, so once again, you're back to a lot of hunger, etc., etc. 1,500 calories. Now, oh, there's no vegetarians. And who goes for carnitas versus barbacoa? Who's carnitas? Who's barbacoa? Hey, I'm a genius. I'd say it's about 50. I'd say that was about 50-50. Okay, that looked like a bit of a joke, but I mean, it's basically a bit like you said in the sense of statistical prediction, right? The thing is that I'm not predicting if Gustavo or Alberto would prefer Coke versus Pepsi. I'm doing it at the level of the population. That doesn't mean to say that I couldn't predict for you or for you. What's the difference? It's this thing about big data. So the thing is that I'm only using one data point in some sense to basically make this prediction. Is to say, hey, your vast majority, almost all Mexicans, you're representative of the Mexican population. This is what Coke and Pepsi sell in Mexico. Therefore, I'll assume that, hey, that one data is good enough. So I'm ignoring the fact that you might actually be quite different. You're all physicists, etc., etc. Or you're all probably more likely to be born somewhere close to here or whatever. But in principle, if I had all sorts of data about you as individuals, I could predict for you as an individual and do a damn good job at it. Meaning I can predict these, to some extent, etc., to a good approximation. I can predict at the individual level. Right? Now that doesn't mean I'm right every time, but the thing is that I can say, it allows me to pick out and differentiate one group from another, right? So in other words, when I put that 70 and 30, I did not say you 70% will be for Coke and you 30% will be for Pepsi. What I said, there will be 70 and 30. Right? But I can build models where I can go, your Pepsi, your Coke, your Pepsi. Right? And that's the thing about data science in the sense of this data revolution. You can start to build models of that type. And it's incredibly inspiring and it's incredibly scary at the same time. Okay, so I will basically go to my conclusions. So basically all science is data science, right? From its very beginnings to the present day, there's just no science without data. But there is a modern notion of data science compared to the traditional idea of data science. And really a lot of it is being associated with, okay, how much data and for what type of phenomena. because of universality, physical systems are relatively phenomenological. You can have big data, so I'm not trying to say that data that comes from certain libraries is small data, but the thing, what I would claim, I think somebody can prove me wrong, but you won't be able to, is that there's no depth to it, meaning this thing of like the city scale and say different. It's just, there's a huge amount of complication. It's like the difference between looking at an interesting photo and go, wow, there's some interesting patterns in that photo. Well, there's interesting patterns that come out of the experiments in CERN, where modern, let's call them machine learning techniques, etc., can be very useful in trying to extract those patterns and the things that we're not used to in physics. But I would never say that one photo, trying to do some image recognition, is the same as describing if you're going to be obese, if you're going to buy Pepsi, etc. So phenomena at one scale in physical sciences are shielded from the rest, and that's why we have this thing called effective theories, where we have molecular physics, atomic physics, nuclear physics, etc. And that's really why we've had a huge amount of success in physics. Complex adaptive systems are phenomenologically deep, and the problem is they need, because they're phenomenologically deep, they need a lot of data to describe them, and that's why things are so new now, because we've never had that data before, and now we're starting to so 1 terabyte data per year, that's about 1 terabyte per person per year. That's more than 1 million books per person per year. Humans can't use or analyze all of that data. So what we're going to do? So there's an universe data. There's a huge potential for good or ill. The question who should have access to it, who should decide how to use. Probably the uses and abuses could be one of the elements of science and politics science and politics in general. Just foreseeable. And finally, the thing about Kelvin back in the late 19th century, they said, right, basically, thermodynamics, electromagnetism, was amazingly successful, and then etc. Is that Lord Kelvin was a very good physicist, but he was proved completely wrong. I'm sure it's not the physicist that Lord Kelvin was, but I kind of feel that in one sense, in terms of let's call it fundamental physics, we kind of pretty much potentially at the not the end of the road, but what else is there to do? In quantum gravity, and that's an amazing deep problem, right? Solve it, well, it's not going to have much impact in the world. Let's call it. Basically, what I feel is that there's a huge amount of data out there to help describe every day, help cure diseases, help people, society be more democratic, be more economically equitable, etc. And the thing is that there's ways of understanding those phenomena, but it goes far, far beyond anything that we've got in physics. We don't have adequate conceptual or theoretical frameworks in which to understand complex adaptive systems or complexity. And what I tried to do was really give some aspects of what distinguishing features are, right? Physical systems are, and complex adaptive systems do. Physical relevant variables. The phenomenology of complex systems is usually more, it's usually richer. Then the other thing is that good science starts with phenomenology and taxonomy, being more moving on to theory. I think one of the problems that we've had with a lot of physicists moving into non-physics fields is once again, using the same old tools, the same old thinking, etc., etc. And the point is you can make progress, but it misses the point, right? And I think what I've been trying to get across here is some of the things that are the point that the physics part is missing. In that sense, often physicists, what they want to do is to say, well, we have theories that apply to the physical world, and the physical world. There should be theories of financial markets, right? There should be theories of this system and that system, the other system. And I think that's, in one sense, usually arrogant. So in other words, if we go back to the example of Brahe, Kepler, and Newton, so the thing is that nowadays there is an inordinate number of Tycho Brahes, right? Every satellite is generating billions, gazillions than Tycho Brahe ever generating. And the thing is, we have a lot of people who think they're kind of Newtons who are going to come up with this theory that describes these phenomena. But I think what we really need is much more Keplers that basically just try to have phenomenological descriptions of systems. And I think that's where data science is, right? So if I wanted to say, hey, data science, what does it do? It's data science is more applied to, let's call it the non-physical sciences in general. But even if you apply it to like CERN data, LIGO data, etc., it's trying to look for phenomenological descriptions of systems rather than true theory. Basically, all this data generated in the data revolution is not scientific, meaning, hey, it's there, it can be used, but it's not done in a laboratory like a clinical trial or something like that. The traditional modeling frameworks of the physical sciences are much less useful in the complex sciences. That's what we're trying to emphasize. That's my opinion. And basically, for people who are interested in big data but want to stay on the physics side, then there are many different techniques. Like I said about machine learning techniques, etc., that can be very, very useful for, say, pattern recognition in a particular problem when you've got data from experiments, whether it's from cosmological experiments or whether it's from particle physics experiments or whatever it would be. And so there's a lot of phenomenological tools that help us be better Keplers. And tactics and also the best way to develop phenomenological and taxonomic understanding of complexity systems. And then finally, so you've all seen this. Archimedes said, I'd like to be able to read the Greek, but I'll give up on that. Basically, giving you a place to stand on, I'll move the idea if you get a lever big enough, you could move any object whatsoever, right? So the exciting thing about the data revolution is the following. It's the idea of giving you enough data and I'll predict anything. Right? It's the idea of just, if I could be big brother in the world with basically data about everything and have enough computing power and smart algorithms to see what the relations were, I think you can predict just about anything. And so, yeah, I think that's it. I'll leave it there. Thank you.
We got time. Also, if you want to ask in Spanish, yeah, I can do it. Quieren preguntar en español, puedo.
Well, I have two questions. Suppose we have a phenomenon, right? And you have a song about that. And I don't know if, in the point of view of a simple system, of a complex system, you can describe it as a simple case of a complex system is.
So I think that's the thing that I showed with the with the fish, right? That's a simple perspective on a complex system. Right? So it's basically like saying the complex system is a whole host of phenomena that are all interrelated and have historical correlates, right? So what I mean by that is the question of why the fish do this. Fish reproduce, fish breathe, fish do a whole load of things that living systems do. Those equations say, hey, okay, if I put this parameter, although I'm not sure what the parameter physically means with regards to fish, we start doing this instead of doing this, right? So that means that that's using physics type modeling, but it's describing one aspect of, but that misses the complexity of the fish, right? So when you say I'm describing when you say I look at perfect, I look at gas. Once you got the temperature and the pressure, you're done, or the pressure of the volume, you're done. So a common read is that you could say, oh, here I have this way to describe the fish building apparatus is this. Is that a complete description of fish? No. Pressure, volume, and temperature is a complete description of the state, just two of them, of a gas. But having those equations is not a complete description of fish. So in other words, there's nothing more to be said about the gas. There's things to be said about the fish.
And the second one is
the second one is if you have a case or example and a measurement of a model to do a supply and complex into a system in the field of view or a simple system. But if you describe it like a simple system or a complex system, and the measurement of the data in bytes, what's the difference? I suppose it's a big difference, but you can tell me an example.
An example of a model or an example of different data? I didn't quite understand.
If you have an example, I will tell you in Spanish. Si tienes un fenómeno y tú lo describes como un sistema complejo o como un sistema simple, la cantidad de data necesaria tú ocupas, ¿cuál es la diferencia entre los dos?
La cantidad de datos.
Ajá, si tú lo has medido, si tú tienes un ejemplo.
Okay. Sí, entonces, right. So let's take the example of like obesity, right? So I can look at the relationship between obesity and say educational level, or obesity and how much you weigh, or obesity and this or that, etc. Just one variable. And what you find is that it's these big cloud of points, meaning there's kind of some kind